Hi, today's class is 2 input NMOS and CMOS NAND gates. So here in this video we are going to discuss about the realization part of NAND gates using N-channel metal oxide semiconductor field effect transistor as well as complementary metal oxide semiconductor field effect transistors. Right. And also we would like to draw the stick diagram for the NAND gates under NMOS as well as CMOS, and also we need to draw the mask layout for this. So up to now we didn't draw the mask layout for any circuits. So in this video we are going to draw the mask layouts. Okay. Next, first, before going to that, first of all let us know about what is this NAND gate. So in digital electronics a NAND gate or not AND, nothing but complementing of AND gate, is a logic gate which produces an output which is false only if all its inputs are true. Thus, its output is complement to that of an AND gate. So what he is saying is this NAND gate is the complementing output of AND gate, and also if all the inputs are true, or nothing but if all the inputs are at logic 1, the output will be at logic 0, which you have already studied in our digital electronics. A low 0 output results only if all the inputs are at high. So if all the inputs are at high state, the output will be 0. In remaining all the cases, the output will be at logic 1. I repeat, when both the inputs are at logic 1, the output will be 0 state. Otherwise, it will be in the at logic 1 state itself. So this is all about the basic about the universal gate of NAND gate. How it has got that name as universal gate means we can realize any boolean function by making use of universal gates. So let us take example. If I want to draw the OR gate using NAND gates, we can realize any type of circuits using NAND gates. That's why it has got that name as universal gate. Now if you go through the stick diagram part, so this is our stick diagram part of 2 input NMOS and CMOS NAND gates. So if you see here, this is the stick diagram of NMOS, this is the stick diagram of CMOS, and this is the stick diagram of BiCMOS. BiCMOS, up to now we didn't have studied that. This BiCMOS implies combination of BJT as well as FET. Okay, so see here under the NMOS, so we have some rules to follow while going to the stick diagrams under NMOS as well as CMOS, so which we have studied in our previous videos also. So let us go through that rules, or let us recall our rules. So under NMOS, the complementing should be represented with a depletion MOSFET. So here, since it is a NAND gate now, a NAND gate means it is nothing but the complementing of AND gate. I repeat, the NAND gate implies the complementing of AND gate. So complementing is there. So we have to go through a depletion MOSFET. So that's the reason I considered a depletion MOSFET here with VGS is equal to 0. I repeat, a NAND gate is the complementing one of AND gate. So here complementing is there. Whenever there is complementing under NMOS, we have to consider a depletion MOSFET under VGS is equal to 0. So the same thing which I have drawn here. So this is our depletion MOSFET when VGS is equal to 0. Right? AND gate. So this is an AND gate. NAND gate means AND operation is there. Under AND operation in NMOS, AND operation means a series of transistors should be there. Whenever it is OR gate, parallel combination of transistors. So it is an AND gate na. So AND gate means a series of transistors should be there. So that's the reason this is a two input one. So I am going to consider two inputs under an AND operation. So that's the reason I am taking these two inputs A and B in series fashion, because it is an and term. Whenever it is OR, we have to connect it in parallel. So no need to worry. Here it is AND. So AND means series combination. So A and B are connected in series with a ratio of 1:2, 1:2. 1:2 and 1:2 are the Z pull up to Z pull down ratios. Okay, which we have discussed that in our previous videos also. Z pull up, determination of Z pull up to Z pull down ratio for an inverter followed by an inverter, as well as inverter followed by an inverter through a pass transistors. So So here the inverter followed by inverter is 1 is to 4 is to 1. So that is represented here, right? Next, in going to the complementary metal oxide semiconductor field effect transistor. So it is a combination of PMOS as well as NMOS. We have already known that. So we need to draw the P combination as well as NMOS combination in this circuit. So the NMOS combination for the AND operation or NAND operation is a series. So that's the reason A and B are connected in series here. A and B are connected in series for the NMOS. So whatever the state pull up one is a PMOS and pull down is an NMOS. So observe carefully. This the pull up one is PMOS here. This is NMOS. Whenever you go for NMOS, this pull up is a depletion and pull down is a enhancement mode. But in case of CMOS, the pull up one is a PMOS and pull down is an NMOS. So for NMOS NAND operation, for NMOS and NAND operation, AND operation is there. So series of transistors should be exist there. So that's the reason I consider two inputs with A and B connected in series fashion. Similarly, the PMOS is a complementary of NMOS, so that's the reason I am connected A and B in parallel here. Since here a series combination is connected, so we need to connect a parallel combination in PMOS. Why? Because this NMOS is a complementing of PMOS. So here series connection of A and B is connected in NMOS, so that's the reason I connected a PMOS in parallel combination. So when you combine both gate terminals, we will get the complementing one. Okay, so this is all about our CMOS circuit. Sorry, this is not stick diagrams. So these are all circuits. These are all circuits. So no, these are not stick diagrams. So circuit. And next, in going to the BiCMOS combination, BiCMOS is nothing but the combination of CMOS as well as BJT. So if you see here the picture very carefully, so this part is similar to this one. See careful here. This part, whatever I am showing with my mouse cursor, this part is the CMOS part, and also additional driver circuit should be there or amplifying circuit should be there. That amplifying circuit is this one. So it is a combination of this BJT as well as CMOS. Okay, no need to worry. We didn't have this by CMOS circuits, but for the reference I am showing here. No need to worry about this. So here BiCMOS is a combination of CMOS as well as BJT. So here see this, whatever the circuit is similar to this one, and to drive this CMOS, one amplifying circuit or driver circuit should be there. This is our driver circuit. This is the driver circuit, and this is our complementary metal oxide semiconductor transistor circuit for a NAND gate. Right. In going to the NMOS NAND gate mask layout. So directly we are going through the mask layout process. So this is our resultant NMOS NAND mask layout. So see, this is our NMOS NAND gate. So first of all, two metal wires are there. So upper part and the lower part. So these are VDD and VSS. VSS are ground. VDD and VSS are two metal supply rails. So that is represented with metal wires. So metals, these are the metals. These are the two metals, and the mask layout for the metal one is represented here. This is the mask layout representation of metal one, as well as this is also metal one. Right. If you go through our previous videos, we studied about the mask encoding also. So for metals, the mask encoding should be like this. So this is a mask layout encoding. This is also mask layout encoding for the metal one. So this is VDD and VSS both are supply rails metal. So that's the reason I considered a metals here. Right. Next one is see here this thing whatever the line. This is NMOS. So totally N diffusion will be there between supply rails VDD and VSS. I repeat, this is an NMOS, so the diffusion will be NMOS. The NMOS, this is NMOS, so the diffusion is NMOS. So the diffusion NMOS is connected between VDD as well as VSS or ground potential. So that's the reason I consider taken a N diffusion between the supply rails from VDD to VSS. This is VDD and this is VSS. So total N diffusion taken, right? And next, in going to the inputs A and B within enhancement mode. So what I said, when this is polysilicon, whatever the color red is polysilicon, green is diffusion, and blue is metal. Whenever there is a depletion MOSFET, definitely implantation should be there. This is implantation, and that implantation should be represented with yellow color, which we have studied in our stick encoding as well as mask encoding in our previous videos, right? So what I am going to do here, these both A and B are enhancement mode channel metal oxide semiconductor field effect transistors. So that's the reason I am going to the enhancement mode here. So when the transistor action is going to take place, if the polysilicon, this is polysilicon, if the polysilicon crosses this end diffusion, this is end diffusion. If the polysilicon crosses the end diffusion, so it makes a transistor action. So the same thing I did here. The polysilicon is crossed the end diffusion here, and also this polysilicon is crossing this end diffusion. So when both this polysilicon crossing the end diffusion, so two transistors are going to exist here, and the transistors input terminals are A and B, which is represented here. A and B in enhancement mode is represented like this in mask encoding. I repeat, I repeat, here A and B are connected in enhancement mode. So when the transistor action is going to be takes place, so both are transistor with it input terminals A and B here. So transistor, when it is going to exist, if the polysilicon crosses the diffusion part, so this is the red color is there. This red color is a polysilicon, and here this red color is also polysilicon, and this green color is there, that is end diffusion. Here the poly is crossing this end diffusion, so transistor existed here, and here also this poly is crossing this end diffusion, so transistor existed here with the input terminals A and B. And what about this depletion MOSFET? So this is depletion MOSFET. The same thing I did here. Under the depletion MOSFET, VGS should be 0. Gate and source should be shorted. Here the gate and source are short circuited. So the same thing I replicated here. The gate and source are shorted here. The gate and source are shorted here with a polysilicon material, and this poly crossing this end diffusion, so it makes a transistor. Here the implantation is there now with yellow color. That implantation shows that this transistor is a depletion MOSFET. I repeat, I repeat, here the gate to source is short circuited. So the same thing I did here. The gate and source are short circuited with the help of polysilicon or red color. And when this poly is crossing this diffusion, so a transistor is going to exist there. So here the transistor existed, but what type of transistor is this? So here the depletion is represented with an yellow color, so that's the reason this is an a depletion MOSFET, or implantation is there with represented with yellow color, right? So this is all about NMOS and NAND mask layout. So if you go through the CMOS, I am going to draw here. So CMOS NAND, CMOS NAND. So I am showing how to draw the mask layouts in our PowerPoint. So see here, I'm going to draw the CMOS mask layout for a NAND gate here. So first of all, this is our CMOS. So I require two metals here. So two metals. So the two metals should be represented with a blue color. So first I am going to take a blue color bar. So blue. So I am taking a blue color here. Why? Since it is a metal, na? Here this is metal. So that's the reason I am considering a blue color. So if you go through this with a dark blue color. So this is VDD, and also I am placing VSS here. So this is VSS. This is VDD. Simply shift to that one. Pull up this one. So this is VDD and this is VSS. So now I need to draw the line, which is a demarcation line here. Now I need to draw the demarcation line. So that should be represented with a brown color. Why I am going to draw here a demarcation line means, why? Since it is a combination of PMOS as well as NMOS, so that PMOS and NMOS should be separated by a demarcation line, and that line should be with brown color. So the I represented with this brown color. Okay, so this is our demarcation line, and this is VDD, and this is VSS. Simply I am drawing the CMOS NAND gate mask layout here with the help of PowerPoint presentation. Okay, next go through the P diffusion. Now I am drawing. I am taking a P diffusion here. Okay, paste. So simply rotate this one. So I want a P diffusion here. Sorry, N diffusion. Under the pull down, there will be a N diffusion. So N diffusion should be there in the pull down part. N diffusion should be there under the pull down part. So we know that N diffusion should be considered with filled with green color N diffusion. So that's why I taken a N diffusion here, and also I require a P diffusion. So just copy this one, copy. So this is our P diffusion. So reduce that size. So this is P diffusion and this is N diffusion, and I require polysilicon. When poly crosses the N diffusion, so transistor is going to exist. So since here, see here, this is PMOS and this is NMOS. So in NMOS, series of transistor. In case of PMOS, it is parallel combination. So parallel means it requires another type. Okay, I need copy, paste. Right. Now I am going to take polysilicon for this. Here I require a polysilicon. So simply copy this one, paste. Next, simply copy this one, Control Z. Just copy this one, paste it. So when I am going to copy this one, we'll get the exact dimensions for both the transistors. And this is polysilicon that should be represented with red color. So represented with red color, and this is also represented with red color. And copy this one, paste here. This is red color. So this copy this one, paste here. Right. So half of the part is completed. So this is our CMOS NAND mask layout. So this is, I am saying that this is VDD, VSS. All the upper part, pull up part is PMOS, and pull down one is our NMOS. So this is a diffusion, poly is crossing in it. This is diffusion, poly is crossing in it. This is diffusion, poly is crossing in it, and this is diffusion, poly is crossing in it. This is input A, B, A and B. So this is combination of PMOS as well as NMOS, right? Next, what I am going to do here is I have to take the P mask. It requires a P mask. This P diffusion requires a P mask. So it requires a P mask. So that has to be represented. P mask should be represented with yellow color. Shape outline yellow. And also we can increase the weight also. So that P plus mask is represented with yellow color here, right? So this is P diffusion and this is N diffusion. So PMOS and NMOS completed. Now let us go with our contact cuts. That contact cut should be represented with a black color. So here contact is will exist. So simply copy all this. Copy, paste. Right. Here also contact is going to exist. At the same point, this contact will exist here also. Right. And also I require some part here. Copy, paste, rotate. Right. So this is our resultant not a resultant one. We will go through the some patterns here. So up to now 75% of mask layout designing was completed. So now I am going to repeat again here. This is our VDD and VSS of metal supply rails represented with blue color here, and this is P diffusion. Here, since it is having P plus mask, which is represented with yellow color, and poly is crossing this poly is crossing this diffusion. So transistor existed here. This transistor is A, and here also poly is poly means red color is crossing the diffusion. So here also transistor existed B here, and this is N diffusion. Poly is crossing in it. So transistor existed here A, and this crossing this diffusion. So here also transistor existed. That transistor is B. Now we will go with some patterns here. We have to represent this with patterns. Otherwise, it's not looks like our mask layout. So go through the patterns. Okay. So we have to go through the patterns part. Format shape. Text fill is there here. Now I'm going to go through the patterns. So more gradients. So gradient fill is there. Sorry, pattern fill is there. So we know that the patterns, right? Now see here, this is our pattern of our metal, right? Similarly, this is also, for this also simply pattern fill metal with some vertical lines. Since both are metal wires, so metal supply rails, so metal one is considered here, and this is P diffusion pattern fill. P diffusion, this is also P diffusion, P diffusion, and this is also P diffusion, and this is N diffusion, N diffusion. This is poly pattern fill, poly. This is poly pattern fill, poly. This is also poly. This is poly. So we completed the pattern levels of this mask layout. Now we have to represent the inputs as well as some dimensions for this NAND gate. So up to now we completed almost designing of mask layout for a NAND gate. Now what I am going to do here is just inserting a text here. This is represented with A color, A, right? And next copy, paste. This is our input B. Simply copy this one. This is our input A for NMOS, and this is also input B for NMOS. This is B input B for copy, paste, B input B for NMOS. So this is our resultant mask layout. If you want to, or if you wish to give any lambda based design rules for this mask layout, you can go that also. Okay, just to simply add the text here. So for metal it is 3 lambda. The minimum width is 3 lambda, right? 3 lambda. So this is a minimum width of 3 lambda for a metal. Simply copy this one and also paste here. So minimum width is 3 lambda for the metal. So for polysilicon it is 2 lambda. Okay. So it is 2 lambda for polysilicon. So for diffusion also it is 2 lambda. So this is diffusion 2 lambda. So with this also we completed the minimum width dimensions of for a CMOS NAND gate mask layout, right? So this is our resultant mask layout for a CMOS NAND gate, and here the transistor existed, and the ratio for this is 1:2, 1:2. We can add that also, pull up to pull down ratios also. If you wish to add, you can add here. Okay, otherwise just leave it. Okay, so this is our resultant mask layout for a two input CMOS NAND gate mask layout. Right. I repeat, this is our see here the circuit of CMOS in NAND gate. So here two supply rails is there. Two supply rails are there. VDD as well as VSS or ground potential, right? And next here this upper part is PMOS circuits and lower part is NMOS circuits. So it is NAND gate and operation is there. So we have to connect a series of NMOS transistor and a parallel combination of PMOS transistor here. So the same thing I replicated here. Two supply rails metals. So I taken a metal combinations with mask encodings like this. So 3 lambda and 3 lambda here. And next I have to connect the PMOS circuits as PMOS mask encoding as well as NMOS mask encoding. So this is our resultant PMOS encoding. So PMOS encoding, and in PMOS it should be connected in parallel combination. So that's why I taken a parallel combination here. So parallel inputs, and in case of NMOS it should be in series. So that's why I taken a series combination here. So this is our resultant two input CMOS NAND gate mask layout. So in the next class we will discuss about two input NMOS and CMOS NOR gates. So thank you. For reference, go through the textbook Douglas A. Puckler and Kamran Ishra again. Thank you.